Hello and welcome back. For this lesson, this is going to be 7.1 Graphing Systems of Equations. You can see this is going to be a 2-day lesson. However, all of the goals and vocabulary are on this page. So you can see right here, we've got 4 goals: determine number of solutions of the system of linear equations, solve systems of equations by graphing, solve linear equations by graphing systems of equations, use graphing calculators to solve systems of equations. Then, of course, we've got the vocab here, which I'm going to show on the next page. Okay, so here we have our vocabulary, systems of equations. This one's actually kind of easy. It's a set of 2 or more equations that have the same variables. Now, systems can have solutions, so the solution of a system is an ordered pair or pairs. This is something you want to point out here. It's an ordered pair or pairs that satisfies both equations. What that means, it makes both equations true at the same time. Now, over here we have a list of the different types of systems. The first one is just a general one. It's called a consistent system. It just means it has at least one ordered pair that satisfies the equations. So anything that has a solution is called consistent. Now, consistent is broken down into 2 further types, independent and dependent. Independent is a system that has exactly one solution. Independent means by itself, so one solution. We also refer to that as a consistent independent. Consistent because it has at least one, and independent because it has only one. On a graph, since we're talking about lines, this would be 2 different lines. The other one is a dependent system. It has infinitely many solutions because it depends on itself. It's also referred to as a consistent dependent. Consistent again because it has at least one. It actually has infinitely many. And it's dependent because they are exactly the same lines. And that means that every x and y ordered pair on one line matches every x and y ordered pair on the other line. And then the last one is just called an inconsistent system. It has no ordered pairs or no solutions that satisfy both equations at the same time. We also refer to this as a parallel system. I sometimes use the word parallel to describe the system instead of inconsistent. And the reason it has no solutions is because the lines are parallel, meaning they'll have no x and y's in common at the same time. Okay, for our first example here, we're going to talk about consistent systems. We want to use the graph to determine the number of solutions the system has. Then we want to state whether it's consistent, inconsistent, independent, or dependent. Well, first of all, you'll notice that these lines over here make up the system. Right there, the y equals negative 3x plus 1, y equals x minus 3. Those are both written in slope-intercept form, but 2 of them considered at the same time is called a system. When you look at the graph, you can see they only cross one time, which means they have one solution. And because they have at least one solution, we call that consistent. Okay, so these graphs are consistent. And then we want to know, is it independent or dependent? Well, it has only one, and independent means one, or by yourself, so independent. So we answer this down at the bottom. It says, since the graphs of the 2 lines intersect at one point, there is exactly one solution. That's what consistent or independent means. Therefore, the system is, we're going to write them both in there, consistent, independent. For our next example, we'll talk about inconsistent systems. So we're going to do the same thing we did in the last one. We're going to determine if the system is consistent, inconsistent, independent, or dependent. First thing you want to notice over here is the slope-intercept form of the 2 equations. And you'll also notice that they both have exactly the same slope. So exactly the same slope means they have the same rise and run, but you'll notice that their y-intercepts are different. This is something you might want to add to your notes. If they have the same slope but different y-intercepts like that, then what we have here are 2 parallel lines, which means they'll never intersect each other. They'll have no solution. So we call that an inconsistent system. Since the graphs of these 2 lines are parallel, or parallel solution, there's no solution to the system. Therefore, the system is inconsistent. Inconsistent meaning doesn't work together. Okay, we want to find out the number of solutions in slope-intercept form. So we're going to do the same thing, state whether or not it's consistent or inconsistent, and if it's independent or dependent. So in order to find out if the system is consistent or inconsistent, the first thing we want to look at is the slope. So up here we have a slope of 6 for this one. And the bottom one we have a slope of 6 as well. So that means this is either consistent and dependent, meaning it's infinitely many, or it's inconsistent. The only way to tell is to look at the y-intercepts. So if we look at the y-intercepts, which are the b values here, you'll notice that the first one is in 10 and the second one is 4, which means these two lines have the same rise and run, but they cross the y-axis at two different locations. Okay, so that means that they are inconsistent. It says because the slopes are the same and the y-intercepts are different, the lines are parallel. The system has no solution, therefore the system is inconsistent. Okay, for our next example, we're going to find the number of solutions in standard form. So we're going to do the same thing, consistent, inconsistent, independent, dependent. However, I am going to suggest a different way of approaching this. Instead of writing it into slope-intercept form, let's use the shortcut version here. So we have a y here, so this would be the b value, this would be the a value, and this is the c value. This is the a value, b value, and c value. So the bottom one is actually in standard form, but the top one's a little out of standard form. But that's okay for this purpose here, because in standard form, the slope is equal to opposite a over b. So this first one is the opposite of a. The a value is -6. So the opposite of that would be 6 over. And then the b value is 4. So 6 over 4. So the first one has a slope of 3/2. I'm going to check the slope of the second one. So the second one has an a value of 9. So the opposite of that would be -9 over. And the b value is -6. So that would be -6. And negative over negative is a positive. And 9, 6 reduces to 3/2. Now, right now, they have exactly the same solution. So that means it's either going to be inconsistent or a consistent dependent. The only way I can tell is by looking at the y-intercept. And remember, the y-intercept, which is the b value, is equal to c over b in standard form. So this first one has a c value of 16 over b, which is 4. So it has a y-intercept of 4, that one. And the bottom one has a c value of -24 and a b value of -6. And -24 over -6 is a +4. So what happens if we have the same slope and the same y-intercept? Well, that means they are the same line, and that means they have infinitely many solutions. So they are consistent. So the first thing is it's consistent. But because it has infinitely many solutions and it's the same line, it means they're also dependent. So it's a consistent dependent system. So if I were to graph that, whatever the lines look like, instead of seeing two lines, you would only see one line stacked on top of each other.